I'm just going to give one more minute until we get to 6:30 before we start this program. Any late stragglers coming in? I know I'm usually one of them. Okay, 6:30. Hello, everyone. Thank you for joining and welcome to Conversations in STEM. My name is Alyssa Menschel and I'm the project's director with STEM Wana Trust and will be the co-host for today. For those of you unfamiliar with STEM Wana, we are a charitable trust whose mission is to engage as many people as we can into confidently and comfortably exploring STEM. Today, I assume everybody here is quite comfortable because we are in our own homes. And I hope at least some of you have put your best day pajamas on. All right, just a little housekeeping before we get started. This is a live event streaming on Facebook and YouTube. You can ask questions. Enter your questions in the chat box or the comment section within your browser window. If we have time, we will try to include some of them during our questions and answers section at the end. For those watching back our recording on STEM Wana's YouTube channel, just shout your question at the screen and I will add them to the list. Just kidding. You are too late. Unless you've figured out the laws of quantum gravity and time travel, which means I have your question already. Perfect. Okay, today I will be moderating this event with one of our very own STEM champions, Chi Wen, as well as a fabulous group of student ambassadors. Tia and Stephen are the wizards behind the curtain, handling the technical support, manning the controls, and pulling in the live questions. Okay, now for the good stuff. We could not be more excited to bring our inaugural Conversations in STEM, Astronomy, Astrophysics, and the Zooniverse with Professor Chris Lintott. Originally, Chris was invited to take part in a very special anniversary tour of New Zealand as part of the Royal Astronomical Society celebrations during April and May. We had partnered with our good friends at Tauranga Astronomical Society and managed to secure a date for Chris to come to our beautiful home, Tauranga. Unfortunately, a global pandemic messed with everyone's plans. However, we were determined to continue on. So we pestered Chris and managed to convince him to join us here today. I am delighted to formally welcome Professor Chris Lintott to be our guest in virtual Tauranga. Chris Lintott is quite an interesting guest. As many of you already may know, he is a distinguished astrophysicist, an Oxford professor, a BBC TV presenter and co-host, a best-selling author, a world-renowned speaker, and co-founder of one of the largest citizen science platforms in the world. Not bad for a first guest. Welcome, Chris. And thank you so much for chatting with us, including all of our friends in Whānau in New Zealand, as well as some friends in the UK that are with us today. We are so appreciative of you letting us into your home in Oxford, England at such an early hour in the morning for you. How are you? And do you have enough coffee?
Well, thank you for the introduction. Yes, don't worry, I've got a cup of coffee and a pot to refill. So I will try and be at my best at 7:30 in the morning. It's not a natural time for an astronomer, it has to be said. Now, I know we've already got lots of questions coming in, so I want to get to those as soon as possible. But I thought it might be useful to talk just a little bit about how I got here and what it is that I do. So hopefully you can see my screen now. This is one of my favorite photos of the night sky. It's taken from New Zealand, showing the beautiful southern Milky Way that will be so familiar to you, many of you, and such a treat for me to see when I do manage to make it to the southern part of the Earth. Really, I want to start here because for me, astronomy started with the simple act of looking up at the night sky. Even now, I think I'm most reminded of being an astronomer when I get back home or step out into the garden and look out the window and look up and see stars and planets there. But the way that I think about the night sky has changed completely in the last few years because we're still making discoveries. And when you look at a night sky like this one, what you should realize is that we now know that almost all the stars that we can see most likely have planets going around them. And so I think of a night sky like this now as a map of a field of view that's filled with countless worlds that one can imagine researching or maybe even imagine one day in the far future visiting. So I can even show you some of those planets. So let's do that. This is a picture of a star called HR8799, which is a terrible name, but never mind. It's not very interesting. And actually, this is an image from a telescope called the Very Large Telescope in Chile. So we're working on the successor to that telescope, which is going to be called the Extremely Large Telescope. But this is merely the Very Large Telescope. But it's a special image because what astronomers have done is take out all the light from the star. So if you just took a normal image, you just see a big blob of a bright star here. That's been taken away, and you can see four little dots around them. They're kind of more easily seen when they move, and this is a sequence of images taken over many years. And those are planets going around a star. So a few years ago, I would have had to show you an animation of this. Every TV program on astronomy has always had the animation of the Earth and Mars and Jupiter going around the sun. This is the real equivalent. Now, most planets we can't see directly. Normally, the star is too bright or too distant to allow us to play this trick of subtracting the light. So we have to find them indirectly. And so here's how we do that. This is a picture of the sun. This is actually a video of the sun taken on a special day from a park just out in the road in Oxford 8 years ago now. And hopefully you can see going across the middle of the sun there, there's a black dot. And that black dot is Venus, the next planet in from Earth in our solar system. And a couple of times a century, Venus passes in front of the sun. And on the right there, what you have is a graph. And this is the world's simplest experiment. When Venus is in front of the sun is slightly dimmer. And that's what the graph is showing. And so even if you couldn't see the picture, if you were in line and you watched the sun, then you'd realize that every time Venus went past, you'd get a dip in brightness. And we play that game. We watch many stars in the sky, usually with little telescopes in space. There's one called Kepler, and there's now one called TESS. And we look for these blinks. And so that process of taking data, analyzing it, is what an astronomer does. I work a little bit on trying to find planets. But I'm supposed to be introducing myself. Here are some of the places that I've been. On top left is University College London, where I learnt to do astronomy. I was an astrochemist, actually looking at the chemistry of star formation. Top right is home now. This is the Dennis Wilkinson building here in Oxford. It's a big concrete building that was built as a particle accelerator, but is now crammed full of PhD students and astronomers. And at the bottom is the Adler Planetarium in Chicago. So I've always worked with people who try to explain what we know about the universe to everyone. And Adler was a wonderful place to do that. But really, my day job is supposed to be not planets, but galaxies. So here are two galaxies. These are relatively nearby. We live in the Milky Way. We saw it on the first slide that I showed you. Milky Way has a few 100 billion stars in, and that's pretty normal for a galaxy. There are 100 billion of these in the observable universe. And these two are medium-sized galaxies, but the kind of problem I work on is to understand their different shapes. So why these galaxies look different. The shape of a galaxy tells you about its history. It tells you about how stars collided, how galaxies have collided, how the galaxy is accreted material from its surroundings. And so sorting out these galaxies by shape is really important. And for the last 10 years or so, we've been asking the public to help us do that. So we put the galaxies up on a site called Galaxy Zoo. You can go there now. It looks a bit different. This is the original design. But if you go to Galaxy Zoo, you'll see an image of a galaxy which perhaps no one has ever seen before. And we'll ask you what shape it is. And we can use that information gathered from hundreds of thousands of people around the world to help us understand the cosmos. And so this method of working, which sometimes gets called citizen science, turns out to be extremely powerful. And when we set up Galaxy Zoo, we were really surprised that I thought maybe 50 people would come and take part, because I'd give a talk like this one and encourage a small number of people to take part. But within days, we had hundreds of thousands of people taking part in Galaxy Zoo. And it's this really powerful collective action. And we found out we could use this for other sciences as well. Other scientists have the same problem we do, in that they've gathered too much data and need help sorting it through. So one of my own favorite projects is this one. This is not an astronomy project. This is Penguin Watch. So my friend Tom goes to the Antarctic every year, and he has a network of cameras that take about 8 million images a year of penguins in the Antarctic. And he's interested in trying to understand how the penguins are reacting to climate change, to fishing, to tourism, and even actually to the effect of Tom going there every year. But he comes back to Oxford with 8 million images of penguins. And he has a very small team. They can't sit and sort through them all. So if you go to penguinwatch.org, you can click and spend a happy half hour contributing to penguin science. And these are, so we've done everything from galaxies to penguins, but we actually have about 100 of these projects, and they live in a place called the Zooniverse. So here's the website. If you go to zooniverse.org now, you find, I think we've got almost exactly 100 projects live at the minute. So from cell biology to trying to find planets, to galaxies, to penguins, to transcribing old manuscripts, if you're more into the humanities than science. There really is something for everyone on Zooniverse, and we've been extremely busy in the last few months or last few weeks as the world has adjusted to the weird situation that we're in. People have really decided that they want to contribute to something together, and people who are lucky enough to have spare time in these difficult times, or kids who are no longer at school around here, are jumping in and making all sorts of discoveries on Zooniverse. And I know that there are teachers on the call, so I wanted to just mention that we have a classroom section as well. So if you want to do Zooniverse with a group, you can go to classroom.zooniverse.org or drop the team a line, and we can point you to the resources we built for that. But let me finish by talking about where we're going. So I'm trying to give the sense that astronomy is now a science about collecting lots of data, whether it's looking for planets or trying to understand galaxies. How much we know about the universe is determined by what we do with the data that we collect. And this is going to be really true in the next few years. So this is a mountaintop in Chile. And on it, you can see there's a building. This is about a year old now. This is going to be the home of the Vera Rubin Observatory. And Vera Rubin Observatory is doing a magnificent thing. We're building a telescope that's as big as the biggest telescopes in the world today. It's got a mirror that's 8 meters across, but it's going to scan the whole sky, the southern sky, every 3 nights and look for, so we can do two things. We can build up deep images and see faint galaxies, but really we'll also look for everything that changes. And so you'll be able to subscribe with your phone to a feed of alerts from this observatory that tell you that things have changed in the sky, that an asteroid zipped past, that a star flickered, that a planet got in the way of its star, that a black hole at the center of a galaxy consumed a gas and flickered on the way in. The trouble is, we know we're going to get about 10 million alerts a night. And in there will be things that we expect. We can probably look for those automatically, but there will also be the unexpected. And whether we make the discoveries that we want to from this observatory, which is costing $1 billion, will depend on how many volunteers we can get to help us sift through that data and be surprised by the universe. So that gives you a flavor of what I'm working on. I'm looking forward to chatting and to digging into questions. Alyssa, I can't hear you. I think you're on mute.
I was trying out my telepathy. My mouth was
I
talking.
can lip read. I'm just not that good.
Okay, sorry. Well, so I was saying you've given us a lot to talk about, and now I think is a great time to move forward with our question and answer segment. So I will hand you over to Chi-Wen and our student ambassadors. Hi, Chi-Wen.
Kia ora, Asa. And kia ora, Chris, and everyone else who's listening at home. Thanks so much for that awesome talk, Chris. It was really, really interesting. I actually had a bit of a play around on Zooniverse earlier today, and I tried out the Eye for Diabetes project, and also spent a bit of time on Penguin Watch as well, because it was fun. I think it's so cool that we can contribute to real research just from our own homes and on our own computers. And I thought it was really easy to use, and like the instructions were easy to follow, and you didn't need to have any special training or anything. So it's great that anyone can do it and kids can do it too. So now we have a number of questions from our students. So to start with, I'm going to hand over to Michaela.
Hi, my name is Michaela. I'm 17 years old, and I'm here with Thomas, Anthony, Michael, and Elliot. We're all students from Otamurai College in Tauranga, New Zealand. My question for you is, what kind of jobs can you get as an astrophysicist?
Thank you. It's a really, really important question. So I think we give the impression sometimes that you study astronomy and because you want to become an astronomer, and that's true for some people. But if you think about how I just described modern astronomy, what we're doing is we're taking data with complex telescopes, we're learning to analyze it, and then trying to find patterns or be surprised by the data. So it turns out those are skills that are much needed by everyone, from machine learning companies to big tech companies to people doing all sorts of business. So most of the students who study with us in Oxford go off to use the skills that they learn with us in business rather than in astrophysics. So if you're used to finding patterns in data on, I don't know, star brightness, then you can probably find patterns in, actually one of our ex-students works for the Royal Mail, so she's trying to find patterns in how postal volumes are changing. And it's the same set, literally the same set of tools. So it's become a very broad route to other things, although I hope that people still keep that sort of sense of wonder that they have from looking up at the sky as well. We need a bit of that, even if you're working far removed from the field. I hope that answers your question a bit.
Yeah, thank you.
Awesome, thanks, Michaela. Our next question is from Thomas.
Hi, my name is Thomas, and I'm 13 years old. If everything started off with a singularity and nothing else, and the only space there was the space the singularity took up, how did it create space out of no space?
First of all, nice background. Can you just move your head so we can see the rest of the galaxy? Cool. Andromeda, I think, but I might be wrong. You can come back now. It's very cool. Hopefully that's bought me time. That's a really difficult question, and I don't know the answer. But let me say some things around it to make it seem like I'm intelligent. So you're right that we have this idea that the universe is expanding. And if you look back in time, that process reverses. So you get to a point where everything in the observable universe is crammed down in a very small point. And if you follow that logic to its extreme, you get the singularity, this point where you have infinite density and no space at all. And we often call that point the Big Bang, because something happened afterwards. The trouble is that we don't really understand that point at all. The fact that if you do the equations in a sensible way, then you find that you predict there's infinite density back there at the beginning. And that's mostly a sign that we don't know what we're doing. It's like if I ask you how many apples there are in the fruit bowl and you tell me there's -6. That's not a deeply profound statement. It means that you don't know what apples are, or that you don't understand the question. And so the singularity is really telling us that we don't understand what's going on there. We know that we need a new theory to properly explain that. There are lots of people working on that sort of thing. So there are people called cosmologists who spend their lives thinking about that very first beginning. And there are some ideas about how a Big Bang could have happened. But we haven't yet got any ideas we can test. There's nothing I can do to look at the universe yet and say something about what happened before the Big Bang. So it's a really difficult problem, but we've come a long way in the last 20 years to understanding the history of the universe, and I hope we'll make some progress. But right now, I don't have an answer to your question, but then nor does anyone else.
Okay. Thank you, though.
I hope that's not disappointing.
Oh, no, it's plenty enough. Thank you.
Awesome. Thanks, Thomas. And thanks, Chris. I think there's something really refreshing around hearing an adult say we don't have the answer.
That's what hooked me on. That's what hooked me on science. When I was 12, I heard a lecture, and the lecturer finished up by saying, "I've told you what we know about the subject, but we don't know very much. And if I come back in 5 years' time, it will all be different." And I thought, this is brilliant. But in this case, I really don't know.
This is great because there's something for the school kids out there to find an answer to when they grow up and become astronomers.
And then they can tell me on Zoom. That would be great.
Awesome. All right. Our next question is from Anthony. Anthony, I think you might be on mute.
Oh, sorry.
Awesome. All good.
Hi, my name is Anthony. I'm 15 years old. My question for you is, do you think the universe will ever stop expanding?
Good question. Just duck your head so we can enjoy the galaxies for a sec. It's very cool. That's M51, an artist's impression of. I'm not sure about the planets, but they look cool too. And there's an explosion in the top left. Okay, you can come back now. This is a great way of me buying time to answer questions. So yeah, so I said earlier the universe is expanding, and there is this question of what happens in the future. And astronomers sort of thought there were three possibilities. So one is that the universe could stop expanding in reverse, and then you end up in the opposite of a big bang, which is sometimes called a big crunch. The other option is it expands forever. And then there's a third option, which is that if you have just the right amount of matter, so you can slow the expansion of the universe through gravity, but not stop it, you get slower and slower and slower, but you never stop. And we think now that we're in the second of those universes. So when astronomers have tried to measure not just how fast the universe is expanding, but how fast the rate of expansion is changing. So we found when this started 20 years ago, people thought they were going to see that it was slowing down. But actually they found the expansion of the universe is speeding up. And so we assume that that's going to keep happening, and the universe will expand forever. And we will end up with this sort of ever expanding future. But we don't understand why the universe is accelerating. So sometimes you hear this idea called dark energy, but that's just it's a stupid name for starters. I don't know what it means for energy to be dark, but it's really just a label for this accelerated expansion. And we don't understand what dark energy is. We don't have a good theory. So because we don't understand it, I can't tell you how it will change in the future. So maybe we just live in a special time in the universe where there's a bit of an acceleration and then things will change. That doesn't seem to be happening. One of the reasons I mentioned at the end of my talk with the slides, that Vera Rubin Observatory on the mountaintop in Chile, one of the big reasons we're building that is that we're going to have a real go at trying to measure whether the acceleration from dark energy is changing over time, because that will help us understand this question. But at the minute, we think it's accelerating, we think it will expand forever, but we don't know why. So that's another problem for you lot to solve in the next few years, please. I hope anyone under 18 on this call is making notes of problems. So far, we've got explain the origin of the universe and then predict the entire future of the universe. If you could do those two things, that would be great. Thanks for the question.
Welcome.
Awesome. Thanks, Anthony. That's quite mind-blowing, I think, to think that it could just keep expanding forever. Like,
yeah.
Yeah.
Neither of the answers make sense, right? It's very hard intuitively to understand something expanding forever. It's also very hard to understand what a big crunch would be like. So at some point, you sort of just have to slightly let go of common sense and trust the universe.
Oh, that's awesome. Our next student ambassador is Michael.
Hi, my name's Michael. I'm 13 years old, and my question for you is, how did our galaxy and our nearby galaxies evolve?
That's a great question. That's more or less what we're trying to work out. So our galaxy seems to be unusual, which is strange. Normally in science, in astronomy in particular, we assume that we're nowhere special. So even before we found all these other planets, people assumed that the Earth was probably a normal planet. It seems odd otherwise. But the Milky Way seems a bit unusual. So one way that most galaxies change and evolve is they collide with each other. You get these big cosmic collisions where two galaxies collide and merge, and they mix, and you end up with one bigger galaxy. But it seems like our Milky Way has had a really quiet life. So from all sorts of evidence, it seems like we haven't had a big merger for a long while. So the Milky Way has sort of done its own thing for a while. It used to, and what seems to have happened, I found out last week, I was doing some work with a friend, Michelle Bannister, who's now in Canterbury, down on your side of the world, and we were looking at papers that predict the Milky Way does this thing where it forms stars and then calms down for a bit, and then it forms stars for another few 100 million years and calms down for a bit. So it has this very regular pattern. But that's going to get disrupted because our nearest big galaxy, Andromeda, and the Milky Way are on a collision course. So in about 4 billion years' time, those two galaxies will collide. And they will form a big galaxy, which my astronomical friends seem to want to call Milkdromeda, which I think is a terrible name. It doesn't have any poetry in it whatsoever. So we're going to end up with this bigger galaxy. But the amazing thing is you can smash these two galaxies together, each of them with a few 100 billion stars, but there's enough space between the stars that the stars there won't be any collisions between stars. But the gas in the galaxies collides and it will trigger star formation, and the whole night sky will light up with new young stars. So in 4 billion years' time, the view will be absolutely spectacular.
Awesome. Thanks for that question, Michael, and thanks, Chris. I wish I could be there in 4 billion years' time to see that, because it sounds quite amazing. Our final student ambassador is Elliot.
Hi, my name is Elliot. I'm 17 years old. My question is, how long do you think it will take, provided we reach a type 1 society, before we can leave Earth and travel throughout the stars?
Gosh. I'm quite so tempted to just say next Thursday and then not elaborate, just for amusement. Thank you for the question. Yeah, I think this is a really good question. I guess we need to talk about what we mean by travel. So let's go full science fiction. So we mean like people that look like us stepping onto the surface of another world, not sending DNA, not building a robot, not sending a probe. Like, let's actually go there. That's the fun thing. I'm not utterly sure we'll ever be able to do that, which is a bit worrying. And I have two reasons for that. One is that all the physics that I know tells me that the speed of light is a really serious speed limit. That while I'd love there to be warp drives and all the rest, my guess is that you can't go faster than the speed of light. So that means that any journey to the stars will be slow. So you're ending up, that's all right. Sci-fi invents hibernation and so on. That's the biologist's problem. They can fix that. But that's going to take a while because biology is difficult. But the other reason I think it may be unlikely is that we don't see evidence for large civilizations zipping around the galaxy. So astronomers are good at spotting unusual things. And if you had sort of grand science fiction empires rising and falling in the spiral arms of the Milky Way, I think we'd see them. We'd see the way they affect their environment. And we don't. So that suggests that either it's very hard to get to that sort of massive galactic scale civilization, or we're already ahead of the pack and we got lucky in that maybe life is rare or intelligent life is rare and we're already ahead. So the optimist view is to hope that we've already done the difficult bit, that maybe getting bacteria started is hard and that we've already done that and therefore we can spread out into this galaxy. But I wonder whether the lack of galactic civilization tells us that that's very difficult. So it's great fun to think about this stuff. And I think it's certainly, I love the fact that we now know we can pick out destinations, right? So we've got the holiday brochure for the first time, and we can say, oh, I really want to go to, there's a star called TRAPPIST-1, which has 7 planets, each of which would look, if you're in the middle planet, it's got a nice temperature, and the other planets would be the size of the moon in the sky. So you can imagine going there. I think what will change this is, I'm giving a whole lecture in about 2 minutes, so apologies. But I think one thing that might change this is the telescopes we're building now, like the Extremely Large Telescope, should be able to test whether atmospheres of planets around nearby stars have signs of life in them. So, for example, you might look for oxygen, and on Earth, the oxygen is produced by life. And I think if we knew that there was a nearby star with a planet that had the right conditions that seemed to have life, I think that would be an enormous spur to at least working out how we can send a probe. Because I think knowing that there might be neighbors would sort of really force our curiosity in that direction. So I think it's going to be an interesting 10 years because we may know that in the next decade or so. So I hope that's a very brief answer to your question, and there's lots to think about there. So thank you.
Thank you.
It looks like we've still got 10 more minutes for student ambassador questions before we move on to public questions. So I'm going to keep going and go back to Michaela for another question.
Hi. My second question is, how do we know the age of our universe?
Oh, that's a really good question. There have been times in astronomical history where we haven't, and that's usually a sign that our theories are wrong. So there are lots of different lines of evidence. And one of the reasons we believe in this crazy model that has the Big Bang and then this expanding universe and all the rest of it, one of the reasons we believe in that model is that the different ways we have of measuring age agree with each other. So one of them is really simple. We have telescopes that can look at very distant galaxies. We know how long the light has taken to reach us from those galaxies, and we see that they look younger. So there's a sort of consistency. If we look at the oldest galaxies we see, they look smaller, and the stars in them are younger. And so that takes us back maybe 12 billion years. So we know from that evidence that the universe is a bit older than 12 billion years. And if you want to falsify the Big Bang model, if you want to disprove the Big Bang, if we found a star that was older than 14 billion years, we understand stars to that extent. So you can check this. So we can also look locally. We can look at stars in the galaxy. We can look at the oldest stars in the galaxy, and they give you roughly the same number. So these are really simple observational tests. The precise number, so we know the universe is 13.8 billion years old, and the error on that is about 100 million years. I like to tease geologists because we know the age of the universe more accurately than we know the age of the Earth. And the reason we know that is that we can see there's light. So if you go back, the universe going back in time, the universe gets smaller, gets hotter, not all the way back to the singularity we discussed. But there's a period just a few 100,000 years in where the universe is opaque. And we can see the light from that time. It's called the cosmic microwave background, which we can still dictate. That light is still flooding through the universe. And by studying that, we get a picture of the universe as it was just 400,000 years after the beginning. And from analyzing that light, we get a really precise age, and it fits in with the simple measures that we make. So there are two examples. There are other ways of doing it, but it's really, we can look at the early universe, we look at the local universe, and the two timescales tie together. The geologists need to get going and sort the age of the Earth out. But in their defense, the Earth is more complicated than the universe. So yeah, great question.
Thank you.
I feel like you're downplaying what astronomers do.
No. We deliberately pick simple systems, right? So this is like, if you want to understand the universe as a whole, you only have to worry about gravity. If you really care only about the big scale and dark energy, which we discussed earlier. So that's two things, right? If I care about, I know, the formation of the Earth, I suddenly have to worry about all the detailed chemistry and the mineralogy and so on. So I mean it when I say the universe is a simpler problem. And one of the ways you know you're an astronomer is that you like simple problems. If you like complexity, then biology and geology are interesting sciences.
Fair enough. Thomas, do you have another question? I think you're on mute, Thomas.
My other question is, what is the most important scientific knowledge we have gained from Zooniverse?
That's a great question. I think the thing, I'm going to give you two answers. So I think the thing I'm proudest of is that if we go back to those galaxies I showed at the center at the beginning, I showed a spiral galaxy and what's called an elliptical galaxy, a big ball of stars. And we weren't the only ones to do this, but I think we were part of a whole bunch of astronomers who realized that there's a difference between the shape of a galaxy and its color. So most spiral galaxies are blue and most elliptical galaxies are red. And the color of a galaxy tells you about the stars that are there now. in particular, the blue color comes from big stars that have just formed in the last few 100 million years. But the shape of a galaxy tells you about its whole history. And so we showed that you can't just use the two interchangeably. Not all spirals are blue and not all ellipticals are red. And that's been really important in trying to understand what's going on. But the most fun we've had has been when our volunteers have found the really unusual and unexpected stuff. They made a proper discovery, said, this is weird, what's this? And my favorite example of that are a set of galaxies called the green pea galaxies. So these were small, round green blobs that some of the volunteers noticed in the background of some of the images. They collected them and they found that they were always the same color. And they were the same color because the light we were seeing came from oxygen gas, which is a sign that these galaxies are forming stars. So these are the best factories of stars in the local universe. They've suddenly decided to turn all their gas into stars. And we don't really understand why that's happening. But we think that maybe every galaxy did this in the far distant past, but the Ps are sort of only getting around to it now. And so they're a way of studying what happened to our galaxy in the past. And lots of people are now studying them, but they were found because a bunch of Galaxies who volunteers said, this is odd. And that's the sort of advantage of having people look at your data. If I can't get my computer to tell me that this is an interesting P-shaped object. And so the Ps have been great fun.
Awesome, thanks for that. Just looking at the clock, and we've got about 5 more minutes, and I think we've still got 3 student questions left.
I'll be fast.
Cool. So who is next? Anthony, what's your second question?
My second question for you is, why do black holes consume all matter apart from positrons and electrons?
Okay, so this is a good question. So a black hole is essentially just a source of gravity. So if you get enough matter in the same place, the gravitational pull will be enough that nothing can escape, not even light. So anything, including particles like positrons and electrons, will fall into a black hole if it gets close enough. But I think you're talking about the fact that this is the great discovery of Stephen Hawking's work, is that if you then just take a black hole and you sit it in the middle of nowhere and you leave it alone, it will slowly evaporate by emitting electrons and positrons. It's called Hawking radiation. And so if you sit a black hole on its own over the very, very long lifetime of the universe, a black hole will evaporate slowly. It's to do with, I'm not going to be able to give a quick explanation, but it's to do with the weirdness of quantum mechanics. So quantum mechanics is the theory that teaches us about the very small and the way that interacts with gravity. Now, we don't know whether this really happens. It's a prediction of the theory. But the problem is that for a decent sized black hole, say a black hole the size of the sun, the mass of the sun, it would take a billion years to evaporate. And so this is quite hard to test in the laboratory. And so we have this theory that this is how black holes work, but we're not sure. So that's a great question. Incidentally, I'm not going to tell you what it is, but there's exciting black hole news coming out later today. So you should, tomorrow morning when you get up in New Zealand, you should check the news. It's not a proof of Hawking radiation, but it is fun.
Thank you.
Cool. I think we're all going to keep our eyes on the news now. Michael, what was your next question?
So my other question is from Charlie, also a student at Otakamai College. And her question is, if you were a teenager in 2020, what things do you think you would find interesting?
Oh, that's a great question. And I have no right to speak for teenagers in 2020, so apologies to all of you. I think it's a great time to be interested in anything, because you have access to experts and the cutting edge in any field. In a way that when I was growing up, we really didn't. And so I think I'm not sure what I'd be interested in, but I'm sure I'd be deep in the weeds reading about black holes or galaxies or the history of football or Greek philosophy or whatever it is. If you're asking what's interesting about astronomy right now, this journey that we're on, going from not knowing whether there are planets around other stars, to now knowing that they're common, to being able to work out what kinds of planets are common, to looking for life, is the most exciting thing. And I hope everyone gets to follow along with that. As a random pitch, one of my friends, Sarah Horst, is in a team which is building a helicopter to go and fly around Saturn's moon Titan. So that's the Dragonfly mission, and I think they're pretty cool.
Thank you.
Awesome. And our last student question is back to Elliot.
We have seen Orion pass over the night sky in New Zealand. My other question is, what do you find is the most interesting observation that you have seen in the Southern Hemisphere?
Well, I love coming to the Southern Hemisphere. I was really looking forward to being in New Zealand, partly to enjoy the skies that you have. I hope you all realise that you get a better view of the universe than we do up here. So the most memorable, I think I've got two memorable nights. So one was recently, I was in Australia at Siding Spring, which is the observatory that's about a 10-hour drive west of Sydney. And there's some little telescopes you can use at the bottom of the hill. So while the professionals were doing their thing at the top, I was sticking my eye through an eyepiece. And there's a massive star called Eta Carini, which, if you've ever seen the Hubble Space Telescope photo of it, it doesn't look like a star at all. Over the last 200 years, it's been nearly the brightest star in the sky, and then it's faded, and then it's come back. And if you look at it, it's two sort of hourglass. It's an hourglass size shaped enormous bubbles of gas. It's a really unstable star, and it will go bang at some point. But I was looking through this medium-sized telescope, and I could see that shape. I could see it wasn't star-shaped. And to connect this image that's so familiar to me, that I've seen in books and on the sky, versus what I could see through the eyepiece, was just stunning. But that needed a telescope. The other night I remember was being in Chile, and at the Very Large Telescope, in fact, and standing outside and just looking at this night sky. And when you let your eyes get used to the dark in a dark site, what you can see is amazing. We had the southern Milky Way nearly overhead. The Magellanic clouds were visible, which we don't normally get to see from here. And it was, I ran into the observatory and pulled everyone else out. And they all sort of shrugged and disappeared back in. And I grabbed the last and I said, "What are you doing? It's this most beautiful night." I said, no, this is normal for us. They're in the middle of the Atacama desert. The nearest streetlights, I think, about 1,000 miles away. And he just had this phrase, which was that good skies are grey, in the sense that if you could see the gap between the stars, it's not a great night. And that's always stuck with me.
Thank you.
Just out of interest, Chris, what advice would you give to someone, say in New Zealand, who wanted to learn more about the sky and what's in it at the moment?
I think the best thing you could do is get hold of even an average pair of binoculars. I think lots of people have sort of old binoculars knocking around. I think people sometimes think you have to buy a telescope, but to learn the sky, binoculars are the thing, because you can scan along the Milky Way, and it doesn't really matter whether you know where you are in the sky. That's a wonderful way to spend an hour or two. The other thing that I did was to just learn a constellation every clear night. So if you get in the habit of going out, and it takes a while to get into, if you can get these star maps online. It takes a while to work out what the scale of the map is versus the sky. But if you start with the Southern Cross with Crux, or something like that, that gives you an anchor, and then you can work your way around the sky. And it doesn't take very long for the sky to become friendly, and then you start to notice how it changes. So I think just getting into that habit of spending 10 minutes outside if it's clear, or even looking out the window, to be honest, and just getting into the habit of looking, and then you start to notice how the sky changes, and that will really reward you over time. But don't feel you have to jump to, I must go to the darkest site in the world, I must buy a telescope. Just I think lazy stargazing is really good for the soul.
Awesome. I think I'll have to go buy myself some binoculars.
Good. Yeah.
Cool. So that concludes our student questions. So thanks so much, Elliot, and the other students from Automotive College for your questions. And thanks so much, Chris, for being open to answering all of them, even the curly ones. So now we're going to take some questions from the public. We've had loads of great questions submitted from our curious audience, and it was really difficult to choose just a few. So thank you so much to everyone for submitting your great questions. So if you don't mind, Chris, I would love to try and get through as many of these as we can with you now.
That's the nicest way I've ever been told to not talk so much. So yes, we'll do a rapid fire round. Yeah.
Okay, cool. So the first question is from Mr. Critchley, a teacher from Mount Maunganui College. His question is, how much of a game changer will the James Webb Space Telescope be for astrophysics?
So great question. So this is a American and European telescope. So it's sort of billed as the successor to the Hubble Space Telescope, but it's got a different job. It's an infrared telescope, and while it will do many things, it's designed to look at the very early universe that we talked about earlier. So the aim of James Webb is to see the first stars and the first galaxies. And I think that will really give us confidence that we've got this story right, that the galaxies at the start of the Big Bang formed and evolved. One of the questions we're trying to answer is how the first black holes formed. We don't really understand that. So that would be great. And then the other area it will make a huge difference in is keeping an eye on some of these planets that we're discovering. So being able to work out what their atmospheres are like. And there's a big row going on at the minute about which planets it should look at. Hopefully it will launch next year, although I think a short delay is possible, but it's going to be really exciting.
Awesome, thanks for that. Our next question is from Jet, who is 11 years old in Wellington, New Zealand. His question is, are we likely to be spreading germs or other life forms to other planets because of our space equipment?
That's a really good question. It is something that people worry about, particularly when we're sending things to places like Mars, where we know life might have existed in the past. People building robots that go to Mars spend a lot of time making sure that they're very clean, and we don't send things to the places where we think life might be most likely to exist. But it's very difficult to be sure. And also in the past, people were much less careful. So it is something we should worry about. But people are very careful to decontaminate and keep incredibly clean these things that we're sending through space.
Awesome, that's good that we're trying to be better at least.
Yeah.
So this question is from Owen in Tauranga, New Zealand, who is just 6 years old and probably one of our youngest viewers tonight. Sky also asked this, and she's 6 as well. I think they're brother and sister. So their question is, are there aliens in the universe?
We don't know. There might be. So we haven't found any yet. And I promise I would say if we had, but so far we don't know, and we're looking. So it may be that we will one day discover signs of aliens, but so far no luck.
Maybe they're just really good at hiding from us.
Astronomers are pretty good at spotting things. I think we'd have found them if they're there.
Okay, that's kind of comforting to hear, I guess.
Yeah. We're also really bad at keeping secrets. It always makes me laugh when people have this idea of a conspiracy theory, but the moment any of my colleagues find anything, they're on Twitter. So
fair enough. So our next questions are about the Zooniverse project. So what are your favorite Zooniverse projects, and what would you recommend school kids get involved with?
Oh, this is like being asked to pick for which is your favorite child. I've got such a soft spot for Penguin Watch. Everyone loves penguins, and so that's been fun. The team behind Penguin Watch just launched Seal Watch, so I spent yesterday learning how to tell the difference between elephant seals and fur seals, so that was fun. And in astronomy, I'm a big fan of Planet 4, which is a project that looks at the Arctic regions of Mars, where all sorts of bizarre things happen. So if they've just relaunched with new data, so I'd recommend Planet 4. I think if you're anyone who's curious, school kid or not, my challenge is go to the Zooniverse website, pick 3 projects and spend 5 minutes on each of them. And my guess is that one of them will hook you because there's something about being able to contribute that's really exciting. So go try 3. There are different projects for different people and different moods. But make sure you come back to Penguin Watch at some point.
Penguin Watch is pretty awesome. It's kind of therapeutic, I think, as well.
Yeah, there's something. I think the task
is
is just difficult enough that it sort of feels like you're getting somewhere. But there are a lot of penguins, and having been to visit them with the Penguin Watch team, they smell absolutely appalling. So they may look cute, but penguins, if you learn nothing else from this talk, penguins smell really bad.
It's probably better to be counting them from the comfort of your own home than in person.
Yeah.
Awesome. So our next question is from Kurt in Tauranga, New Zealand. And his question is, has the reduction in emissions due to the global pandemic had any notable effect on the clarity of imagery from ground telescopes? And if so, have astronomers been capitalizing on the opportunity?
I think that's a really good question, and I don't know what the answer is yet. I haven't seen anyone do a proper study. Actually, most of astronomy has been locked down, so most of our big telescopes have been shut for the last month and a half or so, though some of them are beginning to reopen now. Here in England, we've had this amazing run of very clear, very crisp nights, and from my own experience, I would guess that the lack of pollution has really helped, but we will get proper scientific evidence on that. I know people who are working on it, and we're not sure right now. I'm mostly relieved that in the time that the telescopes have been shut down, we haven't had a supernova go off nearby, or there was a brief false alert about an interstellar asteroid, where we've only seen 2 of those things before. And I'm just glad that the universe has been calm for the last month and a half, so we haven't had to scramble too much.
Awesome. Our next question is from Beatrice, who is 16 years old in Auckland, New Zealand. And the question is, what sacrifices did you have to make that has helped you to get where you are now in terms of social life, family, friends, money?
I don't think I feel like I've sacrificed anything. I don't think you have to have a career. I got lucky in the right job opened up at the right time, but I don't think it's not a case that to be a scientist you have to work 23 hours a day and not talk to anyone. So I don't really feel like sacrificing. It's certainly true that I could get paid more by doing something else, but equally I earn more money than my parents did. So I don't think I have sacrificed anything. I think the hardest thing about doing science as a career is that there's so much science to be done. It's not a job where at 5 o'clock you shut the laptop and you think that you're done. Now, I quite often shut the laptop at 5 p.m. and stop working, but there's always that nagging sense that I could just be doing a bit more, and there's that data to reduce, or that idea I want to follow up. So I think the hardest thing is that sense of never quite being finished. But I don't feel like I've sacrificed much. I've just got lucky and had a lot of fun along the way.
It's great to hear you having a lot of fun doing it. I think it would be really awesome if everyone could find that much fun in what they do. So our next question is from Facebook, and it's from Sky, who's age 8 and who loves space. So the question is, how big is the largest telescope? Is big always better?
Big is always good because the bigger the telescope, the more light you get. And the more light you get, the fainter the object you can see. So the biggest optical telescope that collects the same sort of light that our eyes see has a mirror that is 12 meters across. But the one we're building, the extremely large telescope, has a mirror that's 39 meters across. And I didn't really understand how big that was until I saw that they were talking to people to build the dome, the enclosure that the telescope will sit in. And that thing's basically a sports stadium, because the other place where you need an enormous space with a roof that opens and shuts is in sports stadium. So imagine a very big rugby stadium with a telescope in the middle of it. That's the kind of scale that we're talking about. And we're going to see amazing things. But you also need small telescopes, because when you have a big telescope, you're going to spend a long time staring at particular faint things. You don't do this kind of survey of the sky to find the interesting things in the first place. So I'm a big fan of using smaller telescopes to do creative things. So most of the telescopes that my team use maybe have mirrors that are 2 or 3 or 4 meters across. And we're sort of doing the reconnaissance work that will feed into the very big telescope. So bigger is always better. If you give me more money, I'm going to spend it on a bigger telescope. But we need to be creative about our use of all telescopes as well.
Awesome. That is very big, a rugby stadium size telescope.
Yeah. Suddenly it clicked for me when I realized that.
Okay, I think we're on to our last question, and then we'll need to wrap it up. So the last question is from Alan in Hamilton, New Zealand. And his question is, what do you think will be the next great discovery in astrophysics after imaging a black hole in 2019?
That was fun. We had the Event Horizon telescope that showed this sort of light from the region around a black hole. That was great. It's been an amazing time. We've had these planetary discoveries. We've had gravitational waves, ripples in space, and all sorts of things going on. It's very hard to predict what the next discovery will be. The thing I know will happen in the next few years that is exciting is sort of getting to understand the atmospheres of nearby planets around other stars. So when we get James Webb or when we get the ELT, being able to look at nearby planets, say, okay, this one has an atmosphere like the Earth, this one has an atmosphere that's different. I think that will be really exciting, but I bet we get surprised a few times before then, and that's really exciting. I'm keeping an eye on, there are things called fast radio bursts, sudden flashes of light in the radio sky, and we don't know what those are. And there's a lot of data coming. So I think understanding those is a big challenge too. And that's a fun story to keep an eye on.
Cool, thank you. And thank you to everyone who submitted your great questions. New Zealand is known for being a nation of curious and creative thinkers, and the responses tonight have proved it. So thank you everyone for your contributions and for getting involved. And thank you so much, Chris, for answering all of these questions. So I'm now going to hand back to Alyssa.
That was great. There were so many interesting conversations just then. It was such an exciting back and forth between communities, and I felt like the students were so well thought through questions. It was fantastic between black holes and beginning of the universe and citizen scientists and lots of telescope talk. That was just fantastic. So we now have tons to think about and hopefully explore further. But now we all do have to go to bed, and we do have to let you, Chris, get on with the rest of your day. It's still morning for you, even though it's nice and dark for us. But before we sign off, I just want to give a few quick thank yous. We would like to thank Mrs. Blears Woodcock, aka Mrs. BW at Otamotai College, for all her help in organizing our student questions. And a big thank you to our student ambassadors. You were fantastic. Thank you very much. I think Elliot would like to say a few words.
On behalf of the other student ambassadors and Otamotai College, we would like to thank you very much for taking time out of your day to talk about astronomy and astrophysics and the Zooniverse with us.
Thanks, Elliot. And a big thanks to our STEM champion, Chi Wen, for all her help behind and in front of the camera. And of course, many thanks to you, Chris, for joining us and entertaining all of our questions. And I hope you had as much fun as we did. You've been such a great first guest for our conversation in STEM, and you have set the bar very, very high for our next event. For the benefit of everyone that's watching now, you can now see on the screen details of Chris's book, useful links, resources on how you can start your science journey. And if Chris has inspired you with getting into astronomy and the universe, we would highly recommend getting in touch with our friends at the Tauranga Astronomical Society, or contact the Royal Astronomical Society of New Zealand to find one close to you. They both have Facebook pages that you can connect with. We will also have these details on our website, as well as a recording of this event. Go to stemfest.nz. Feel free to share this and any of our resources at stemfest.nz with friends and family. And everyone, stay safe, kia kaha, and we hope to see you all soon. Bye for now.